I'm going to go over the basics of chemical equations and how we write chemical equations, and then later on we'll get into types of reactions. So in a chemical equation, it's describing what's happening in a chemical reaction. And in a chemical reaction, we have one or more substances that will react, and you'll make one or more new substances. And we know that they're new substances because these will have their own unique chemical and physical properties. So we've made some sort of new chemical substance. When we're writing a chemical equation, we often write our reactants on the left side. That's pretty standard. These are the things that are being used in our chemical reaction. And then the products are written on the right side of our chemical equation, and these are the substances that are being made or produced. We'll know what the reactants and products are chemically by looking at the chemical formulas that are written on the left side versus the right side. So if one of my reactants is carbon dioxide, you would see that indicated by CO2 being written on the left side of the equation. And the last thing is we balance our chemical equations in order to satisfy the law of conservation of mass. So I'll go through that further on in these notes. So some of the symbols that you'll need to know in order to write or read a chemical equation. The first one is phases of matter. So there will be 3 phases of matter that you'll see written in a chemical equation. And then there's actually a fourth, it's not really a phase, but a fourth indicator of what, a fourth indicator of, it's not a phase, but a fourth indicator of how we observe this chemical to be. So the 3 are solid, liquid, and gas. So those ones we're pretty familiar with. You'll see those written as subscripts in parentheses after you write the formula of your substance. The fourth one is aqueous. So it's not really so much a phase of matter. It's more of the fact that we observe it being dissolved in water. And so a really good example of this is NaCl. So that's salt. So you can have salt that is solid, that's like table salt, or sometimes if your salt is dissolved in water, they'll write NaCl aqueous, and that tells you more so that these sodiums and these chloride ions are floating around in water. The next thing you'll see in our chemical equation is arrows. The arrow represents the term produced or yield. It tells us that our reactants have created something new. So CO2 plus H2O produces, and then we would use the arrow. Some of our reactions later on, or some of the reactions that you might see, might use a double arrow, one pointing back toward the reactants and one pointing toward the products. This just means that the reaction is reversible, and that just means that the products can then react with one another and reform the reactants. Sometimes you'll see the arrow drawn like that. I get really lazy and I draw my arrows sort of with these like half arrow lines sometimes, but basically you'll see arrows pointing in both directions. A couple of other symbols that we'll see is either this delta sign or the word heat, and that just tells you that heat needs to apply in order for the reaction to occur. Or sometimes you'll see a substance written above the arrow, and that typically tells us that there is a catalyst being used. And a catalyst is a substance that helps speed up a chemical reaction, but it's not actually used up. So what ends up happening is, let's say I'm using this manganese oxide in order to help speed up a reaction. The reality is that manganese oxide will also exist at the end of the reaction. So it doesn't actually get used up, so you don't write it on the side of the reactants. And it doesn't get made, so you don't use it on the side of the products. But the fact that it exists within the test tube helps the reaction, whatever it is, actually take place. And so that's what a catalyst is. And that's where you'll see catalyst written in a chemical equation, is above that yield arrow. All right. So let's look at an example of a chemical equation. Here is one for photosynthesis. This is 6 CO2 in gas phase plus 6 H2O in a liquid phase produces or yields C6H12O6, which is glucose sugar, in a solid phase, and 6 oxygen gas. So let's talk specifically about all the information that is here. So when I look at this chemical equation, what I see is I see the reactants on the left side. And my reactants are carbon dioxide, gas specifically, and liquid water. So those are my two reactants. My products are on the right side of my equation. So I have a glucose molecule, a solid glucose molecule, and I have oxygen gas that is produced. Those are my products. When I look at my chemical equation, I see that carbon dioxide, based on this formula here, is composed of 1 carbon atom and 2 oxygen atoms. So let's say that's my 1 carbon atom. Here are my 2 oxygen atoms. So here is my carbon dioxide. The carbon is bonded to those 2 oxygen atoms, so these atoms are tightly bonded to one another. That's what a CO2 molecule would look like if I were writing it as like a particle diagram. Now, based off of the law of definite proportions, if I'm saying that carbon dioxide is a reactant, I can't change this number here, because the law of definite proportions says this compound exists in these specific ratios. So 1 carbon to 2 atoms is the ratio that makes up carbon dioxide. So once you know what this subscript is, you can't change it. It produces glucose, which is made up of 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. And remember, once I know what my chemical formula is, these numbers cannot change because this is what makes it glucose. This ratio of these atoms is what makes this compound. All right. So in nature, in order for this reaction to actually happen, you're going to need 6 molecules of CO2. So that's what this 6 represents. I need 6 CO2s in order to make glucose, because glucose requires 6 carbon. So in order to have 6 carbon, I'm going to need 6 of these molecules. And that's why we end up having to balance our chemical equations. So the law of conservation of mass basically says matter cannot be created or destroyed in a chemical reaction. It can only be changed. So what we mean by that is that in a chemical reaction, bonds are broken, atoms can be rearranged, and new bonds can be formed. But atoms cannot just magically disappear or magically appear. So all the atoms that existed at the beginning of the reaction, those same atoms have to exist at the end of a reaction, but those atoms can be bonded to other atoms, to atoms that were previously bonded to something else. So the number of atoms and type of atoms that exist on the reactant side must also equal the number and type of atoms that exist on the product side. So again, no atoms can just magically disappear or appear on either side of the equation. That also means the mass of our reactants will equal the mass of our products, because if 6 carbon exist on the left side and 6 carbon exist on the right side, then their masses should be the same. So even though carbon was bonded, so our C6, 6 CO2, and our H2O, I think it's 6 H2O, make our glucose molecule. And our oxygen. So if this is our balanced chemical equation, if you count up your atoms here, I've got 6 carbon, and I've got a total of, this is 12 hydrogen, and I've got, let's see, Right here I've got 12 oxygen plus 6 more, so that's 18 oxygen on the left side. And when I look at the right side, I've got 6 carbon here, 12 hydrogen, and I've got, this is 12 plus 6, I've got 18 oxygen. So the mass on this left side, right, is going to be equal to the mass on this right side, because all of my atoms that existed on the left side also exist on the right side. So that's basically the law of conservation of mass. And in order to satisfy the law of conservation of mass, we balance our chemical equations. And by balance, I mean we indicate how many of each molecule, how many of them have to exist in order for the reaction to actually take place. So let's look at another example of this. Here we have 2 H2s, so here's one and here's your second one. React with 1 oxygen gas molecule and you make 2 H2O. So here's your first one, here's your second one. And that means that all of our atoms are going to be accounted for. So there's 2 oxygen atoms on both sides. There are 4 hydrogen atoms on both sides. So all of our atoms are accounted for on either side. And this only works when we balance our chemical equation. So it only works if you have 2 H2s and you make 2 H2Os. Because if I only had 1 H2, if this one were gone, right, I wouldn't have enough hydrogen to make the second hydrogen, or the second water molecule. If I don't make the second water molecule, then one of these oxygen right here are not accounted for. So this only works when I have 2 H2, 1 O2, and I make 2 H2O, because that helps account for each atom. All right, when I read this, I can actually read this in 2 different ways. You can read it as though you're talking about just molecules. So 2 molecules of hydrogen react with 1 molecule of oxygen gas to produce 2 molecules of water. We can also talk about it in terms of moles, and I know we haven't talked about moles in a long time, but remember 1 mole is a unit of measurement that is equal to 6.02 times 10 to the 23 of that thing. It's a lot like saying a dozen, right? So you could say 2 dozen molecules of hydrogen react with 1 dozen molecules of oxygen to produce 2 dozen molecules of water. But dozen in the terms of atoms and molecules still isn't very much. So oftentimes we talk about them in terms of moles. And again, since these are all ratios, like you're making a recipe for something, I can also refer to this chemical equation in terms of moles. So 2 moles of hydrogen molecules will react with 1 mole of oxygen molecules to produce 2 moles of water molecules. Because now that is the ratio of these things that I need in order to produce my product. Oh, also note that the number 1 is assumed if you don't write any coefficient in front of your molecule. All right, one more example here. So here we have propane reacting with oxygen gas to produce carbon dioxide, water, and we produce heat in this particular case. So 1 molecule of propane right here, so again that 1 is assumed. 1 molecule or 1 mole of propane reacts with 5 molecules of oxygen to produce 3 molecules of carbon dioxide and 4 molecules of water. Or again, you could say 1 mole of propane reacts with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. So again, this is now the ratio in which you need these in order to make your products. All right. We balance our chemical equations in order to satisfy our law of conservation of mass. All the atoms that existed before must exist at the end of our reaction. Therefore, the mass at the beginning of our reaction must equal the mass at the end of our reaction. We can only change the coefficients. We cannot change the chemical formulas. And these coefficients show us the relative amounts of reactants and products in order for our chemical reaction to occur. I'm going to go into more practice on our worksheets, and we will be talking about types of reactions. But the last thing that I want to talk about in these set of notes is the difference between endothermic and exothermic reactions. So endothermic reactions are reactions that absorb heat. And so endothermic reactions, heat is often written on the reactant side. So we don't put any like minuses in our chemical equations. We only use the plus symbols or the arrows. So in order to indicate that energy is used up in your reaction, we put heat on the reactant side as though it is a reactant in order to create your products. So endothermic reactions are reactions where heat goes into the reaction. That means heat is absorbed. And we'll indicate that by writing heat on the reactant side. So when you think endothermic, you can think N, which is like in, and that means that heat goes in to the reaction. Exothermic is when heat is produced, and if heat is being produced by the reaction, we write it on the product side. So this means that heat is being released. And if we look at the name exo like exit, so heat is exiting the reaction. That means heat is being released or heat is being produced.